we have ions, okay? Bonds are made of, the bonds are between ions, okay? So, in chapter 5, you read that the main group metals tend to lose electrons, okay? And others tend to gain electrons. Now, this is what we know as ions, but ions can either be positive or negative. Positive like cations, for example. Positive is, cations are positively charged ions. Remember, cations are positive because cats are always positive. Cat, ion, cation. Then we have the anions, okay? Anions are those ions that are negatively charged. And onions are negative because raw onions taste bad. That's the only reason I could imagine. Because for me, onions, for example, are amazing. But I understand understand and I know that there are a lot of people that hate onions. Okay, so you can relate it. Okay, you can relate cations, always positive. Nobody hates cats. Okay, I understand that part. But onions, you can actually assume that they're a negative thing because people don't like it when it's raw, probably. So this is a key that I give you to memorize the two kind of ions that we have, positive and negative, and the positive are called the cations because of the cat thing, okay? And anions are because of the onions. Just relate those two words and you'll be okay. About those are the kind of ions, okay? And now these are the type of chemical bonding, okay? We can have two type of chemical bonding, ionic and covalent, okay? So chemical bonding that results from the electrical attraction, remember this, electrical attraction between cations and anions. So when the positive and negative are attracted to each other, we can call that kind of bonding ionic. So take a look at the image right here, okay? So we have atoms A from the element A and atoms from the element B. So what happens when they join? As you can see, they are forming a bigger substance, and this substance is made of the two electrically charged things, negative and positive. And when these are attracted, we call this ionic bonding. Then we have the other type of chemical bonding, which is called covalent. It says that it results from sharing the electron pairs between two atoms. You're going to see what sharing means in chemistry. So, in this case, you have two atoms, okay, element C and element D, and they are joined together. But as you can see here, they are not showing you a specific charge. And that is because of something that I am about to teach, okay? Now, take a look at this and how is this related to the Lewis structure that we know so far. As you can see here, I have the Christmas tree for chemistry. Okay, chemistry. Yeah, I'll stop about the jokes. So we have I know I can't stop when I begin, but I will, I promise. So you can see, for example, here, I'm telling you, let's build a Lewis structure for sodium, for argon, and for bromine. Okay, you can do it in your notebook. You can do the Lewis structure for sodium and tell me how it looks like. Only the Lewis structure, okay? And then you tell me how is the Lewis structure for sodium. Sodium
It has one
one dot, right?
electron.
One electron in the outermost level, which means one dot. Okay, so I'm gonna put it here. That's the Lewis structure, okay, for sodium. Then I say, okay, let's do one for argon. It should look something like this. Okay, argon, which is number 18. Just make sure that everything I'm showing you here makes sense, okay? Because it has a purpose. Is my Lewis structure
electrons?
8 electrons. So because there are 8 electrons, you put the 8 dots around the argon symbol. And the other that I have is bromine, okay, which is number 35. If you build the electron configuration and then the Lewis structure, you realize it is something like that. 7 dots because we have 7 electrons in the outermost level. Is that right? Now, just make sure that bromine's Lewis structure makes sense, okay? I have 7 electrons in the outermost level. Now take a look. There's another thing that I wrote, and it is that sodium is a metal. I also wrote that bromine is a non-metal. So in this type of bonding, in ionic bonding, we are going to have combination, for that saying, of both metal and non-metal. The reason is because the metal is always going to act like a cation with a positive charge, and the non-metal will act like anions, okay, like anions with a negative charge. The reason is the following. Okay, in the case of sodium, sodium has one dot, which means one electron in the outermost level. Bromine has 7. So all elements in the periodic table want to look like the noble gases. Take a look here. Argon is a noble gas. Just imagine that argon is the element any other element want to become, okay? It's like an ideal role model for elements. So take a look here. Sodium wants to look like argon, and bromine also wants to look like argon. Now, answer me this question. If you were sodium, what do you think is easier for you? Do you think it's easier to lose one dot or one electron? And do you think it's easier? Okay, you have two options. Because you are sodium, you have two options. The number one is you lose one electron, and the second option is you gain 7 electrons. Okay? Imagine that you had to pay for those electrons with energy. What do you think is easier? To lose one electron or to gain 7 electrons?
To lose one?
Lose? It's easier to lose one electron, that is true. Okay? Now, if you were bromine, what do you think is easier? To lose 7 electrons or to gain 1 electron?
Gain
One.
one.
Okay, so you understand the concept of gaining and losing very well. Congratulations. And yes, the reason is easier because sodium needs a lot of energy in order to get 7 electrons. Imagine that sodium has to pay for that, for those 7 electrons. It's a lot of energy for sodium. So sodium says, nah, I give up. I give up. I give 1 electron away because it's easier. In bromine, instead of selling the 7 electrons, says, I better buy 1 electron. I just need 1 electron, so I better buy it. So imagine that you now in your electron configuration for sodium, you get rid of your last electron. Okay? No, it's not. Okay, sorry. You get rid of your last electron. Erase it. Erase it from the electron configuration. Erase the last electron for sodium. And tell me, now, after giving away 1 electron, how many electrons does sodium have in the outermost level?
8.
8.
Aha! Remember, noble gases have 8 electrons. All of the elements want to become noble gases. Which means, in other words, that they need to accomplish 8 electrons in the outermost level. Sodium, by giving 1 electron away, now it has the electron configuration to be considered a noble gas. And that is the stability that all elements need to accomplish. Now, what about bromine? Bromine gains 1 electron, okay? And what happens now?
It has a
It's
electron.
gonna have 8 electrons in the outermost level. So you understand the idea? Elements, atoms in this case, are gonna try to sell, okay, or to buy electrons, but they consider to be easier in order to look like noble gases. Of course, they are not noble gases, but they just want to look like, because looking like noble gases is going to give them stability that they need. Okay,
Every noble gas has 6 electrons, right?
8. Take a look, argon. Argon has, I know, wait. Argon has 2 plus 6, which makes 8. 2, 2, 2, and 2. So all noble gases except helium have 8 electrons in the outermost level. So this type of bonding in chemistry, when you have a metal combined with a non-metal, is called ionic. And the reason that this bonding exists is that the elements want to look like noble gases. So take
Miss,
a look. Tell me.
that in bromine gain 1 electron is -1.
Exactly. That's what I was going to say. So sodium, because sodium lost 1 electron, in this case, in chemistry, losing is considered to be a positive thing, okay? So sodium, which is the metal, the one that loses electron, that is a cation. So because it gives 1 electron away, the charge for sodium is positive. Positive, the amount of electrons that it lost, that is positive 1. Now, take a look in your periodic table. What is the oxidation number for sodium?
One.
1.
1. So all of this is related. Now take a look to bromine, and now it's mind blowing because you will take a look to bromine and you will notice that it has several valence electrons. In my periodic table, I have plus, minus, 1, and 5. But in the case of ionic bonding, bromine uses a charge of -1. So when you combine elements and the type of bonding is ionic, I mean combined metal and non-metal, bromine or non-metals are going to have a negative charge. Now, this is just the introduction. We're not doing the compounds yet. We're just seeing a type of bondings. But as you can see, all of this is related to the electron configuration. Belen?
Miss, and these chemical bondings are like not just like imaginary, I can say. I mean, they can happen in real life, those chemical bondings. I mean, you can you know, combine sodium with bromine.
It's possible. All these combinations are possible. But you need to have a lab, and you need to buy the pure substance. That is the most difficult thing, because pure elements are not easy to get. I mean, I can get hydrogen easily somehow, but the rest of the elements are very hard to get. Well, helium, for example, that's the one that we use for balloons. That's easy to get too as a pure element, but most of the elements are not easy to get in their pure state, so it's very difficult to combine. But if you are a chemist, for example, or you study chemical engineering, for example, yes, you're gonna get used to work with those elements, and it's possible. It's not like imaginary. In our notebook, yes, it's going to be imaginary, but it is possible in real life. Yes, you cannot visualize the bonding, and if that's the question that you have, that if you can see it through a microscope, for example, is very difficult. But there are some other things, like for example, molecules, really large molecules, that can be visualized through the microscope. Not through a regular microscope, but yes. This is a homework that I assigned for these 4 elements. Okay, very easy to work with. It says build the ECN, tell how many electrons are in the outermost level, draw the Lewis dot structure, and calculate the charge. Okay, for example, how did we get the charge? Sodium lost 1 electron, so the charge is +1. Bromine gained 1 electron, so the charge is -1. So you're gonna work with these elements, and then you will classify them as cations or anions. This homework is just for practice. Belén?
Yeah, Miss, sorry that I'm bothering too much, but so we're going to know all this with those elements and their noble gas that it's like that, like the electron configuration with noble gases, right?
Yes, for example, oxygen. Take a look. Oxygen is number 8. So oxygen will tend to gain electrons, and the charge is going to be negative something. Okay? And then when oxygen gains the electrons, is going to look like a noble gas. You will see what noble gas oxygen is going to look like. But I don't want you to compare it to noble gas, but you will see that the structure is going to be very similar to one of the noble gases in the right. If you want, I'm gonna try with one exercise for you to see how to work in your homework. Okay? It doesn't cost points, but I'm going to work with it. So I'm gonna work with. Let me see if it's not in the presentation. Let me see. Oxygen, carbon, magnesium, boron. Okay, I will work with selenium, which is number 34. I will work with selenium. Sorry. Let me see. Okay. Okay, so selenium, which is number 34. If I have to build the electron configuration, just let me bring it for here. This tree I need it every day in my life, you know. So I'm gonna put it here. And I will build the electron configuration, which is 1s2, 2s2, 2p6. And then I continue. 3s2, 3p6, 4s2. Now I have 20 electrons. So I need to go on because I need 34. So 3d10, which is 30. 4p.
4p4.
Okay, so it will be 3d10 and then 4p4, 34. Okay, so this allows me to see that in the outermost level I have 2 plus 4, 6 electrons.
6 electrons.
So if I build the lowest structure, it's going to be Se 1, 2, 3, 4, 5, 6. Okay. So then I ask, is it easier for selenium gaining electrons or losing electrons?
Gaining
So
2 electrons.
gains 2 electrons. So this gives me a charge of 2 negative, or negative 2 is the same, of negative 2. And then I have to classify selenium. Selenium is going to act like cation or anion.
Anions.
Anion. That's all I have to do with selenium, for example. So you have to work with those 4 elements that are very, very simple. And I just want you to work with that. I mean, to tell the number of electrons, to draw the lowest structure, and then analyzing gaining or losing electrons to become a cation or an anion. That's this little homework. It doesn't cost points. I just want you to practice. Though you still have to send it. Now, ionic or covalent. This is going to depend on the element's electronegativities. Remember that the other day we were discussing about the electronegativity. Okay? So, bonding between atoms of different elements is rarely pure ionic or purely covalent. So, the type of bonding that exists in the example that I did here between sodium and bromine, this is very hard to occur. Okay? So, we have some kind of bondings that are in between, and that is going to depend on electronegativity. The electronegativity is a measure of the atom's ability to attract electrons. So the more electronegativity something is, the more electronegative an element is, an atom is, we say is more attractive. So it's going to attract electrons. Fluorine, which is the element that has more electronegativity, is going to attract more electrons. Now, the degree to which bonding between atoms of two elements is ionic or covalent can be estimated by calculating the difference in the electrons in the element's electronegativities. Now, take a look to this. We have the table of the electronegativity, the one that I showed you the other day, and we have, well, this key. I'm gonna call it a key. Okay. So, fluorine, as I told you, is the most electronegative element. So the idea, okay, is that I tell you, for example, tell me what kind of bond is going to exist between potassium and chlorine, for example. Okay, so the the idea the idea is that you have to subtract. This is what I wrote over here. Okay, can be estimated by calculating the difference between the elements' electronegativities. Okay, calculating the difference is subtracting, okay, the electronegativities between the elements. So I say, okay guys, let's work with potassium and chlorine. So we need to subtract. That's a procedure that we must do for electronegativity. Okay, so it's going to be chlorine, which has an electronegativity of 3, is going to subtract potassium that has an electronegativity of 0.8. How much is that?
2.2.
2.2. Then you're gonna take your key. This is the key, okay? And you will locate where 2.2 would be. Is it going to be here in A? Is it going to be in B? Or is it going to be in C? In what section is 2.2 going to be?
A.
It's going to be more or less here, right? But it doesn't matter where you put it. In fact, the only thing that matters is that you classify that type of bond. So, a bond between chlorine and potassium will be ionic. Okay, so you have just to classify the type of bond. Now, if I tell you between strontium and tellurium,
Will be negative 1.1.
Nonpolar.
okay, it doesn't matter if it's positive or negative, okay, just the number. So it's going to be 1.1 or negative 1.1. In the end, you're going to locate it in what portion? In A, B, or C?
B.
B.
It's going to be in B. So it's going to be more or less here, okay? And then, what kind of bond is that? It's polar covalent.
Polar covalent.
So if it is negative, we will take it like a positive number.
Yes, you take it always as a positive number. And I'm going to leave the topic here. and we're going to finish next class. So I'm going to send you a homework where you have